All right, so the next lesson in your series of summer lectures is on biostatistics. Now, I know that sounds like it's boring, but I promise you it's super interesting. It's really interesting, I promise. I gained an appreciation for biostatistics when I had to actually analyze my own data when I was in grad school. And it's actually, it's kind of like taking math and applying it directly to problems that you have, which is really what math is all about, because otherwise, what's the point of it? So I always like to start with this hypothetical question. Now, what this is a bar graph looking at the effect of 3 different fertilizers on the growth of one plant. So if you look here, if you follow my pointer, right here is the control group, and we have fertilizer 1, 2, and 3. This shows the average plant height, the mean plant height of those plants after 4 weeks of planting and allowing them to grow. So I was always asked, which do you think works the best? Take a minute, not a minute, it should take you a second to figure out which one you think works the best, and you should probably say fertilizer 2, which is this one right here. Okay. But let me give you some more information. I want to see if you have the exact same kind of idea, or if you believe the same thing. Not that belief really matters in science, you need data. So let's look at that. The data table showing the height of 6 plants in each group. C is the control group, as we said before, that received a sham fertilizer, which wasn't a real fertilizer. And now we have the raw data. And I want you to look at them, and I want you to tell me which one do you think probably works the best now. So I'm going to give you a few seconds. You can pause the video if you want, if you really want to look at the data. And one thing should kind of come to mind when you look at it. So the previous graph graphed just the means of the plants, or the average of the group. Okay. When we look here, though, there is, so if we look at the control group, notice how close together those values are. If we look at F1, the values are all over the place. The same thing's true with F2. You have this very large value here, and this very small value here, and kind of like intermediate values here and here. Whereas F3, we have consistency throughout. 9, 8, 7, 9, 9, okay? And that consistency is important, okay? So now if I asked you which one do you think probably works the best, hopefully you would change your answer to F3 if we look at the two together. So you'd say, oh yeah, F3 probably works better because what? There's less variation in the data. The data is more consistent, okay? But here's the thing. Your opinion doesn't matter in science at all. You can't just allow a human to look at data and try to analyze it with your eyes. What we have to actually do is run statistics on it. We use a program on the computer, or you can do it, some of them by hand. Okay, because these opinions that you have change from person to person. How can you say, oh, that one I think works better? And you could rationalize it by saying, oh, there's less variance or there's less spread in the data, but you wouldn't actually have a concrete kind of number to say, yes, this looks good. So what we need to do in science is actually come up with that concrete number. And the way we do that is we do statistics. Data that we have is nothing without statistical analysis. You can look at it, you can see trends, so you can get an idea of what your data kind of means, but you can't actually make any conclusions from that data because we bias. Whether purposely or not purposely, we will bias our data. And that's a big problem. We don't want to skew our results and our conclusions based on our preconceived notions of what we think should happen. So before we get into the more complicated stuff, I want to go into the things that you probably learned in elementary school, or at least middle school, which are mean, median, and mode. And they give you very different information that you probably haven't really thought about. You just thought, oh, I'm going to do this. I know how to do a mean. Oh, mean's an average. So, and almost everyone kind of understands what a mean is. But a median gives you very different information than a mean does. And mode gives you even other information than the median and the mean do. So and they're appropriate depending on the different types of data that you actually look at. Okay, so your mean is the one that we tend to focus on the most in science because it's used in a lot of different statistics. So this is the equation for it. I know it looks kind of complicated, but basically it is you just add up all your values and divide by the total number of values that you have to give you an average of what you get. The median is the middle value. So a difference between mean and median I like to do is the average income level in the United States of a family. I don't have the numbers on me exactly, but if you took the mean income, that is a much higher value. Okay, let's say the mean income in the United States is like $50,000 per family, maybe a little bit higher, I don't know. But the median income, because the wealth tended to pool a little bit more at the top, the median value is much lower, probably in the 30s to 40s. So they give you different information. So what that would tell us is that the average is not actually an accurate representation of what most people make, where the median value would give us a little bit better idea of what that means. Common values, how frequently something occurs, is also a very important thing. So that is where mode comes in. And this kind of relates to mode 2, is a bell curve. Now, I think a lot of you have probably heard of a bell curve before in different math classes that you've taken. Basically, it's this idea that most things, when they fall, if you take like any type of characteristic that they have, they kind of fall on a bell curve, which looks just like this. It's called a normal distribution, where most people fall right around the average. So height would be an example of this. And then you have people that are outliers, who are either really tall or really short. Most people are this big, right? Within this kind of 95% of people fall within this range. IQ is like that as well. The average IQ is around 100. You have people who are above average, and you have people who are below average. But most people are right around 100. If you're out here, you're in your gifted ranges, and over here you get your geniuses, which are much more rare. So that's kind of what a normal distribution is. And in order to do that, basically it talks about as I said, the frequency of the number of individuals that exist that have that particular attribute. This is also called parametric data if it falls within a normal bell curve. So any of you that take statistics will probably learn a little bit more about what that means. We're going to start to talk a little bit. Here's showing you IQ, right? Average is 100 on this test. You have the top 2% have an IQ of higher than 130. The bottom 2% have an IQ less than 70. Okay, but most people are right around between 85 and 115. Most people that exist. Same thing with height. Height tends to skew this way. Men are a little bit higher than women. But they both show this normal bell curve kind of thing. Okay, variance. And we're going to come back to the bell curve in a second because we're going to talk about standard deviation, which actually relates to a normal distribution as well. Variance measures the spread in the data. So we could actually, if we looked at our fertilizer data, which we will, you actually can measure how much spread or how much those points differ from the mean. So if they're all right around the mean, you'd expect those points, the variance, to be very low. Whereas if they're all over the place, you have really high values and really low values, and your mean's kind of in between there, you'd have a lot more variance. And that's what this statistic actually shows. So if you see, this is your individual point, okay? So let's say your mean is 6, okay? And let's say this was a 12. So you put a 12 here minus the mean, which this stands for the mean, the line over this x. So this would be 6, this would be 12. You square it. Notice the farther away this point is from the mean, the larger this value is going to be. So you're actually going to increase the value of your variance. N is actually equal to the number of total points that you're testing. So if you have a sample size of 10, N would be 10, minus 1 would be 9. So as I said, it takes the mean, it compares each data point to it, and squares it and divides by the number of total points, minus 1, blah, blah, blah. So that gives you your variance, which is a measurement of spread. You want to know that. We can then take the variance, and then we can create a standard deviation from the mean for that. And that's going to be a very useful statistic for us. If there are values that are far away from the mean, you get more spread, more variance, and that's a higher standard deviation. So all we're doing is we're taking a square root of the variance to give us the standard deviation. If all are very close to the mean, you'll have a low standard deviation. Now here is an important point. 95% of all data points will fall within 2 standard deviations from the mean. Okay? 68% of data points will fall within 1 standard deviation of the mean. Okay, so when you calculate it, that means if you have very little spread, your actual bell curve is going to be very skinny. Okay, if you have lots of spread, the bell curve is going to be much flatter than it normally would, but it would still have that normal shape. Not the last, but one of the major important ideas that you have to understand is this concept of creating error bars on your data. So this will take the standard deviation and divide it by the square root of the number of samples taken. So it's just another thing that you have to do, but let me explain the whole point of it. It basically will take our mean and compare it to the actual population mean. Do we think that based on all the spread that we have in our data, are we actually getting something that is representative of the real population? If we were to take, like for example, I measured 10 plants. If I were to take every plant on the entire planet that is of that species that I was testing and measure it, how close would my mean be to that to the actual population or mean? So when you graph your mean, that's not enough, as I showed you guys with that first example I gave you, which let me go back to it, what I mean. Right here. This isn't enough. We have to be able to talk about the spread, and we want to include that information on here. So what we're going to do that is actually include error bars. And what error bars do, let me go back down too far. If you do +1 or -1 standard error and you add error bars, there's a 68% chance that the true population falls within the range that you put on that graph. It'll make more sense in a second when I put it on there. If you do 2 standard errors from the mean, so you do the standard error calculation and you would just multiply it by 2, and then you put the bars on, plus or minus whatever that value, there's a 95% chance that the true population falls within that mean. And that 95% number is very important, or less than 5% chance that it could not be within there. And that tends to be the way science works, is in that 5% chance that it may not be, could be explained by chance alone or randomness. So if our mean is 10.5 and our standard error is 0.25, then there's a 68% chance that our true mean falls between 10.25 and 10.75, plus or minus 10.5 plus or minus 0.25. And you put the error bars in there to actually show that. If we do 2 standard deviations from the mean, which is what we almost always will do, there's a 95% chance that the true population will fall within 10 and 11. Does that kind of make sense? Because now, if one standard error is 0.25, that means 2 would be 0.5. So if we subtract 0.5, you get 10. And if you add 0.5 to 10.5, you get 11. And this is how we'd actually graph them. Here's showing you the mean of the bar graph, and then you put the error bars in like this. Okay? So this is just showing plus or minus 1 standard error from the mean. If we did 2, you'd get a different value. So the way we like to do this is, now I know this is only 1 standard error of the mean. You're always going to do 2, unless it says otherwise. Okay? If there is no overlap between the 2 treatment groups' error bars, so notice there's no overlap here, that means we can say that they are different enough statistically to be actually considered different values. The problem is, if you have overlap, the true mean can fall anywhere between these 2 values here, if you follow my pointer. So that means the true mean could actually be up here, and the true mean of this could actually be up here. And if that's true, they're essentially the exact same thing. So there's no real difference between them. Is that, hopefully that makes sense. Again, if you have any issues, you can email me over the summer. I can help you out. But we don't want overlap, because overlap means, depending on what we're looking for, but if we're trying to figure out if these 2 things are different, you don't want overlap. Overlap means that they are not statistically different between their error bars. Error bars can also be found on line graphs, as you can see here. This is actually out of an old AP Bio practice exam, and it shows you the bigger the error bar, the more spread there is in the data. The smaller the error bars, the higher probability that we fall within that range. Okay, so they'd ask, like, which 2 of these would be considered actually different amounts? Notice this first one has tons of spread, but because this last point and this point their error bars don't overlap, these 2 points could be considered statistically different. These 2 cannot. This one can be, I think. If I draw it over, yes, this one can be statistically different from this, but this one is not statistically different from that because their error bars overlap. Hopefully that makes sense. Okay. When we graph bar graphs, we graph them when we have non-continuous data, so like grouped data. Okay. We'll do line graphs if the data is continuous, meaning that there's some relationship between the different points that we graph. So this is the number of spots over the course of months. We're going to see how the spots increase as months go on. Okay. Bar graphs, as I said, are for categorical data, usually control versus experimental group, and comparing the two. Okay. This idea of significance in science. So you're going to want to start to learn this language, and we're going to use it throughout the year, is that results need to be statistically significant to be accepted as different by peers. So what that means is, and I told you this before, our threshold is there's a 95% chance that randomness cannot explain our data. That's kind of what we said. Or there's only a 5% chance that it could. Okay. Now, we call it a p-value, so it's going to be called the p-value of 0.05. Our value has to always be, when we do statistics, our p-value. We're going to get statistical descriptive values, but we use a chart to convert them into p-values. P-values have to be less than 0.05, which means there's less than a 5% chance that randomness could explain the results.